NEC Article 250.64e addresses the specific requirements for bonding metal raceways that contain grounding electrode conductors, often referred to as GEC. The primary purpose of this section is to ensure that the metal raceway itself does not impede the flow of fault current and that it remains at the same electrical potential as the grounding electrode conductor it houses. This is particularly important when the raceway is not inherently bonded at both ends through listed fittings or other approved means. The underlying principle is to maintain a low impedance path to ground. If a fault occurs within the raceway or the grounding electrode conductor comes into contact with the raceway, a substantial amount of current could flow. If the raceway is not adequately bonded, it can create a high impedance path, leading to voltage potential differences and potentially dangerous touch voltages. Article 250.64e specifically states that the bonding conductor used to bond the metal raceway to the grounding electrode conductor must not be smaller than the grounding electrode conductor itself. This means that the size of the bonding conductor is directly tied to the size of the grounding electrode conductor. If the grounding electrode conductor is a certain size based on the requirements of NEC Table 250.66, then the bonding conductor must be at least the same size. The rationale behind this requirement is to provide a path for fault current that is at least as good as the path provided by the grounding electrode conductor. The grounding electrode conductor is sized to carry fault current back to the source, and the bonding conductor serves to ensure that the raceway does not become an impediment to that fault current flow. To illustrate this with an example, consider a scenario where a building has a service entrance with a 2000 amp service. According to NEC Table 250.66, if the service entrance conductors are larger than 1100 kcmil copper or 1750 kcmil aluminum, the grounding electrode conductor is required to be a minimum of 3/0 copper or 250 kcmil aluminum. Now, suppose that the grounding electrode conductor is run within a metal raceway for a portion of its length. If that raceway is not bonded at both ends through listed fittings, then a bonding jumper is required to bond the raceway to the grounding electrode conductor. According to NEC Article 250.64e, that bonding jumper must be at least 3/0 copper or 250 kcmil aluminum, matching the size of the grounding electrode conductor. The NEC does not permit the use of a smaller bonding conductor in this scenario. The intent is to eliminate any potential bottleneck in the fault current path. By requiring the bonding conductor to be at least the same size as the grounding electrode conductor, the code ensures that the raceway remains at the same electrical potential as the grounding electrode conductor during a fault condition. The NEC also provides specific rules regarding the materials and installation of grounding and bonding conductors. These rules are intended to ensure that the conductors are mechanically strong, electrically continuous, and resistant to corrosion. Grounding and bonding conductors must be securely fastened to the grounding electrode and to the equipment they are intended to ground or bond. The phrase "not bonded at both ends" is also crucial in the interpretation of NEC Article 250.64e. If a metal raceway is properly bonded at both ends using listed fittings, such as bonding lock nuts or bushings, then a separate bonding jumper may not be required. The listed fittings provide a low impedance path between the raceway and the enclosure or equipment to which it is connected. However, if there is any doubt about the effectiveness of the bonding provided by the fittings, or if the fittings are not listed for bonding purposes, then a separate bonding jumper should be installed. Moreover, it is important to distinguish between grounding and bonding. Grounding refers to the connection of electrical equipment and systems to the earth, while bonding refers to the connection of different metallic parts of a system to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety, but they serve different purposes. In the context of NEC Article 250.64e, the bonding conductor is serving to bond the metal raceway to the grounding electrode conductor. This ensures that the raceway is at the same electrical potential as the grounding electrode and that it does not impede the flow of fault current. There are a few additional considerations to keep in mind when applying NEC Article 250.64e. Firstly, the bonding conductor must be installed in a manner that minimizes impedance. This means that the conductor should be as short and straight as possible, and it should be securely fastened to the raceway and the grounding electrode conductor. Secondly, the bonding conductor must be protected from physical damage. This may involve installing the conductor in a conduit or other protective enclosure. Thirdly, the bonding conductor must be accessible for inspection and maintenance. This means that the conductor should not be concealed behind walls or ceilings. Furthermore, it is essential to consult the specific requirements of the NEC in the jurisdiction where the electrical work is being performed. Local codes may have additional requirements or amendments to the NEC that must be followed. In summary, NEC Article 250.64e requires that the bonding conductor used to bond the metal raceway containing a grounding electrode conductor to the grounding electrode conductor must not be smaller than the grounding electrode conductor itself, when the raceway is not bonded at both ends using listed fittings. This requirement is intended to ensure that the raceway does not impede the flow of fault current and that it remains at the same electrical potential as the grounding electrode conductor. By following the requirements of NEC Article 250.64e, electricians can help to ensure the safety and reliability of electrical systems. To delve deeper into practical scenarios and common pitfalls, consider the following points. One frequent question arises when dealing with multiple grounding electrodes. In situations where a building has multiple grounding electrodes, such as a ground rod, a water pipe electrode, and a building steel electrode, the grounding electrode conductor must connect to all of these electrodes to form a comprehensive grounding system. If any portion of the grounding electrode conductor run to these various electrodes involves metal raceways, each raceway must be addressed according to Article 250.64e. This means that each raceway, if not bonded at both ends via listed fittings, requires a bonding jumper size no smaller than the grounding electrode conductor. Another area of concern often involves existing installations. Older electrical systems might not have been installed according to the current requirements of the NEC. When upgrading or modifying such systems, it's crucial to assess the grounding and bonding to ensure compliance with current codes. If a metal raceway containing a grounding electrode conductor in an existing system is found to be inadequately bonded, the necessary bonding jumper must be installed to bring the system up to code. This might involve retrofitting a bonding jumper to an existing raceway, which can sometimes be challenging depending on the accessibility of the raceway. The choice of materials for the bonding jumper is also important. While copper is the most common material for grounding and bonding conductors, other materials, such as aluminum, are permitted under certain conditions. When using aluminum bonding jumpers, it's essential to ensure that they are properly terminated using listed connectors suitable for aluminum. Aluminum conductors can corrode if not properly terminated, which can increase the impedance of the bonding path and compromise its effectiveness. Furthermore, the method of connecting the bonding jumper to the raceway and the grounding electrode conductor is critical. The NEC specifies that bonding jumpers must be connected using listed connectors or by exothermic welding. The use of improper connectors or methods can result in a high impedance connection, which can defeat the purpose of the bonding jumper. It's also worth noting that the NEC provides specific requirements for the protection of grounding and bonding conductors. Grounding and bonding conductors must be protected from physical damage and corrosion. This can be achieved by installing the conductors in a conduit or other protective enclosure, or by using conductors that are specifically listed for direct burial. The inspection and testing of grounding and bonding systems are also essential. After installing a grounding and bonding system, it's important to inspect it to ensure that all connections are properly made and that all conductors are properly sized and installed. It's also a good practice to test the impedance of the grounding and bonding system to verify that it meets the requirements of the NEC. One common mistake that electricians make is to assume that a metal raceway is automatically bonded simply because it is connected to a metal enclosure. While a metal-to-metal connection can provide some degree of bonding, it's not always sufficient to meet the requirements of the NEC. The NEC requires that metal raceways be bonded using listed fittings or by a separate bonding jumper. Another common mistake is to use the wrong size of bonding jumper. The NEC is very clear about the size of the bonding jumper that is required for metal raceways containing grounding electrode conductors. The bonding jumper must be at least the same size as the grounding electrode conductor, unless otherwise permitted by the NEC. In conclusion, the proper application of NEC Article 250.64e is crucial for ensuring the safety and reliability of electrical systems. This article specifies the requirements for bonding metal raceways that contain grounding electrode conductors, and it's essential for electricians to understand these requirements in order to install safe and effective grounding and bonding systems. By following the guidelines outlined in this discussion, electrical professionals can mitigate risks associated with fault currents and contribute to the overall safety of electrical installations. To further illustrate the practical implications of NEC Article 250.64e, let's consider some specific scenarios that electricians might encounter in the field. Firstly, imagine a situation where the grounding electrode conductor is routed through a section of rigid metal conduit, or RMC, to protect it from physical damage as it exits the building. The RMC is connected to a metallic enclosure at one end, but the connection at the other end, say, to the grounding electrode itself, is not a listed bonding connection. In this case, a bonding jumper is required to connect the RMC to the grounding electrode conductor. This bonding jumper must be sized no smaller than the grounding electrode conductor itself, as per Article 250.64e. The jumper ensures that the RMC remains at the same electrical potential as the grounding electrode conductor, providing a safe path for fault current. Secondly, consider a scenario where the grounding electrode conductor is run through a length of electrical metallic tubing, or EMT. EMT relies on set screw or compression fittings for its mechanical and electrical connections. While these fittings can provide a good mechanical connection, they are not always listed for grounding purposes, especially in larger sizes or under fault conditions. Therefore, if the EMT is used to protect the grounding electrode conductor and the fittings are not explicitly listed for grounding, a bonding jumper is required, again sized according to the grounding electrode conductor as per Table 250.66. Thirdly, think about a situation involving a service disconnecting means that is located some distance from the grounding electrode. The grounding electrode conductor is routed through a metal raceway for part of its length. If the raceway is not bonded at both ends with listed fittings, a bonding jumper is necessary at the non-bonded end. In this case, the bonding jumper would connect the metal raceway to the grounding electrode conductor, ensuring a continuous low impedance path to ground. These scenarios highlight the importance of understanding the specific requirements of NEC Article 250.64e and of carefully evaluating each installation to determine whether a bonding jumper is required. It's not enough to simply assume that a metal raceway is automatically bonded. A thorough inspection is necessary to verify that all connections are properly made and that the raceway is effectively bonded to the grounding electrode conductor. The NEC also addresses situations where the grounding electrode conductor is installed in multiple metal raceways. In these cases, each raceway must be bonded to the grounding electrode conductor in accordance with Article 250.64e. This means that if there are multiple raceways, each one must have a bonding jumper size no smaller than the grounding electrode conductor. Furthermore, the NEC provides guidance on the installation of bonding jumpers. Bonding jumpers must be installed in a manner that minimizes impedance and protects them from physical damage. This can be achieved by using short, direct bonding jumpers and by protecting them with conduit or other suitable enclosures. The NEC also requires that bonding jumpers be accessible for inspection and maintenance. This means that bonding jumpers should not be concealed behind walls or ceilings, and they should be readily accessible for inspection and testing. The proper application of NEC Article 250.64e is not only essential for safety, but also for compliance with the electrical code. Electrical inspectors will typically verify that metal raceways containing grounding electrode conductors are properly bonded, and failure to comply with the requirements of Article 250.64e can result in a failed inspection. Moreover, it's important to stay up to date with the latest revisions of the NEC. The electrical code is revised every 3 years, and changes are often made to the grounding and bonding requirements. By staying informed about the latest code changes, electricians can ensure that their installations are safe, compliant, and up to date. In addition to the technical aspects of NEC Article 250.64e, it's also important to consider the practical implications of these requirements. Installing bonding jumpers can add to the cost and complexity of an electrical installation, but these costs are justified by the increased safety and reliability that they provide. By properly bonding metal raceways containing grounding electrode conductors, electricians can help to protect people and property from the hazards of electrical shock and fire. The bonding jumpers provide a low impedance path for fault current, which helps to trip circuit breakers and clear faults quickly. This reduces the risk of electrical shock and fire, and it helps to protect electrical equipment from damage. In conclusion, NEC Article 250.64e is an important part of the electrical code that addresses the bonding of metal raceways containing grounding electrode conductors. By understanding and following the requirements of this article, electricians can help to ensure the safety and reliability of electrical systems. The key takeaway is that when a metal raceway houses a grounding electrode conductor and is not bonded at both ends via listed fittings, a bonding jumper no smaller than the grounding electrode conductor itself is mandatory. This measure ensures a continuous, low impedance path to ground, safeguarding against potential electrical hazards.